Our next speaker is Ben Pierce, who will be discussing an innovative project that utilizes big data and sophisticated statistical methods to proactively identify high-risk crash locations on his presentation, leveraging non-traditional crash factors to predict future fatal and life-changing crashes. Before we begin, we want to extend our sincere gratitude to all many conference sponsors. Their support makes this event possible. Make sure to check out their sponsorship page at the event app for more details. And then I'd like to introduce Ben Pierce.
Got to have my fan. It's a little too hot here in North Dakota for me. I'm from Cleveland, and I was pleasantly surprised with the balmy weather you're having. Today I'm going to talk to you, I'm going to tell you a little story. We're going to go on an adventure. Like any good story, there's a hero, there's a villain, there's some adversity. We'll talk about some speed bumps along the way. We'll talk about hubris and ego and the trouble it can get you into, and all sorts of good things. So sit back and come on this little adventure with me. I only have one requirement. You must laugh at all of my jokes, or this would be the longest 50 minutes of your life, okay? That was not a very good laugh. We'll work on it, okay? If you don't laugh at my jokes, we're going to be here a while. I know they're not funny. I've been told that many times. I don't care. Laugh anyway. Makes me feel good. All right, let's see if we can do this two-button thing. Victory. So our journey starts a long time ago, and my boss was sitting in a district office, and they were lamenting the fact that we've been doing this drive to zero now for 10 years, 15 years, and we're still driving to zero. And we've had a lot of success, but there's still a lot of people that seem to be dying on the roadways. And my boss said, well, I know a guy. He's a statistician. I'll bring him in. Okay. So I joined the next meeting, and we were talking, and I said, well, you know, we have this traditional approach that we use to analyze safety. And it goes like this. Crash happens. We collect information about the crash. We do a forensic analysis of what happened, what are all the movements that happened that led up to the crash, right? This car came this way, this car came this way, right, et cetera, et cetera. And eventually we say, hey, car ran off the road and there was a fatality. Well, and then we put our engineering hats on, or more correctly, you put your engineering hats on because I'm not an engineer, and we say, hey, that car ran off the road and flipped over and a person died. If we would have had something like a cable median barrier, that wouldn't have happened, right? So then we say, well, if this happened here under this condition, so this road segment had a certain AADT, it had a certain number of lanes, it had a certain lane width, let's install cable median barrier here, but let's go look everywhere else that looks just like this segment and install cable median barriers there. We solved that problem, right? That is the traditional safe systems approach that we use, at least in Minnesota, for how to decide where to do crash treatments to prevent fatalities or serious injuries, right? So that's what I had in my mind when I was sitting in the district office after my boss had just got done saying, well, he's a statistician, he can solve this. You know, no pressure, right? So I, in my infinite wisdom, said to the district engineer, I said, well, one of two things is going wrong here. Either you don't have enough data or the right kind of data, or you're not using the right statistical model. Because he kept saying, well, all these crashes seem to be happening randomly, right? We do all this safe systems, and we do these forensic analysis, and we go fix this. We put median cable barriers on, and blah, blah, blah. And then we get a fatal crash on a roadway over here that we weren't expecting. It's random. So this is where the hubris part comes in. I said, well, nothing's completely random. You just don't have enough data yet, or you're not looking at it the right way. Yeesh. Which is an effectively true statement, but one that can get you in a lot of trouble, as I'm about to explain. So don't ever say that to anyone ever again. That's the first lesson of today. Don't ever say all you got to do is get more data or look at it a better statistical model, because you will launch yourself on an endeavor of a lot of work, which if you're a workaholic, that might be a good thing. Oh, now we got to work on the joke thing, right? This is audience participation. We're just in the very beginning of our 50 minutes. Okay, that's your first warning. So what do? Well, the easiest thing to do is go out and get more data, right? So we set about getting as much data as we can get our grubby little hands on. We started to get from third-party vendors information on speeds, from cellular data. We got weather data from NOAA, from the RWIS sensors. We got all kinds of land use data. We got data from the State Highway Patrol on what citations that they've issued on a given road segment over the course of 7 years. We've got derived data, so we figured out from the citation data and from the crash data how often a State Highway Patrol officer was present on that segment of a roadway over the 7-year period. We calculated how curvy every road was. We calculated how much change in elevation there was. We calculated everything we could think of. And I had to write this number down. I had to recalculate it before this. We ended up with 1,345,851,360 records. Take that, big data. 1.3 billion records. And we knew everything there was to know about every segment in these two counties, two districts in Minnesota. One's an urban district and the other's a little more rural. And I said, okay, we got the data, right? Can't really think of too much more to add. Maybe there's a few variables we left out. But if you're thinking to yourself, well, did they look at this roadway variable? We did. It's in there, okay? If you're thinking, well, did they look at how close the school was? We did. It's in the data. Did they look at how many establishments serve alcohol along that road segment? We did. It's in there. Did they look at how much alcohol was served? We did. It's in there, okay? So we looked at and included just about everything we could think of, and a few things that we didn't think of that somebody else thought of, we put it in, okay? 1.3 billion records. So what's next? Well, if we've got a big data set, let's use big boy statistical models, right? We're all hearing about this AI phenomenon, right? Let's just throw AI at it and see what happens. Let's go and use some sophisticated negative binomial or other general linear models, and let's use a hierarchical Bayesian model. Very sophisticated, and I guess going from the left to the right, what we have is a very unstructured model kind of system, which is AI. It just kind of figures out the patterns in the data, all the way to the right, which is the Bayesian approach, which is very, very structured. And a pain in the ass, but it's very structured. So over the course of about 6 months, we ran model after model after model after model after model. And what happened? Well, a lot of heartache, a lot of disappointment. And I'm from Cleveland, so I should be used to it, right? Every year we're going to win the Super Bowl, and every year our hopes are dashed and crushed. But the models didn't fit. Not a single one of those variables that we pulled in seemed to have good explanatory power to predict locations of where fatal or severe crashes are going to happen. The models didn't converge. And at the end, we had nothing, right? Even the AI model didn't really work. Yes, we got an algorithm out of AI. No, it didn't make a hill of beans sense when we looked at it. It did kind of predict locations where fatal crashes happen, but the directionality of the variables and it just didn't make sense when you look at it. So if we were to put our blinders on and use AI as a black box, we maybe could have made something of it. But I couldn't explain to anybody why that model was saying what it said. I would just say, just put your data in and you'll get an answer at the other end, right? And that's really not that useful when we go to the next stage, which is how to operationalize what we're finding. Well, in this case, we didn't have anything to operationalize. So, now what? I just spent 6 months, a lot of money, a lot of time. Client's not happy. My boss isn't happy. I'm not happy. We got to do something else. So I started thinking to myself, okay, what are we going to do? And I distinctly remember sitting in my office thinking, well, let's go back to the drawing board. What do I think is related to fatal crashes? Right, I got 1.3 billion records, every data element I can think of under the sun, and none of it panned out. So let's go back to the beginning. I either missed some data or I'm not doing the right statistical analysis approach. So I'm going to ask for a little audience participation. How many of you think that there's a relationship between speeding and fatal crashes? Just show of hands. Where were you when I needed you? How many of you think that there's a relationship between seatbelt use and fatalities? Older or younger drivers and fatalities? You see, these are not trick questions, so if you're not, DUI? Reckless driving? Yeah. So what I did was, and I didn't think of all of those, maybe because I'm not an engineer, but what I did was I came up with a logic model, right? So I said, well, how do each one of these variables that I have in my data set impact another variable, which eventually, working our way from left to right, predicts fatal or serious crashes, right? So I would say things like, well, if the roadway width is 11 feet or 12 feet, it usually means then speeding the speed would be higher, right? Which would then predict crashes, which would then predict fatal crashes, right? So I built this whole complex logic model. And I started along the pathways of, okay, I'm going to use my Bayesian structured approach and I'm going to model every one of these arrows. And then I was sitting there 2 days after Christmas, about a year ago, and I was talking to my wife. I was complaining. I wasn't really talking, I was complaining. And she said, well, isn't speeding the big factor for fatal crashes? And I'm like, well, yes. And she goes, well, isn't drunk driving? And I'm like, yes. And she goes, what about the age of the occupant? And I'm like, yes. She goes, seatbelt use? I'm like, yes. And she goes, why aren't you using them in your model? And I looked at her and I said, because. Because, damn it. So I pulled up my logic model and I walked her through it and I explained how this factor, influenced that factor, influenced fatal crashes, right? And she goes, well, why don't you just start on the right instead of on the left? And I thought, First, I didn't think, First thing I thought of was, don't tell me how to do my job. I'm a professional. I'm a statistician, damn it. But I took her advice, which I usually do, and I decided, hey, what if I threw in to the model factors that were associated with driver behavior or driver characteristics? And I just used those factors. Okay, so that's what I did. I said, how can I get factors, how can I get information on speeding behavior? Well, I could look at citations, and I could pull out the citations that are associated with speeding, right? for a given road segment, and I can say, well, this road segment had a lot of citations for speeding, or that road segment had not so many citations for speeding. Or I could look at crashes and say, this crash was caused by speed, or this crash was not caused by speed. And I started with citations because, again, I'm an idiot, and I should have started with crashes, but I started with citations, and what I found was road segments where there's an overabundance of citations for speeding generally didn't have fatal or severe crashes. And that puzzled me for a while until I figured out why that was. Well, it's because the State Highway Patrol was doing what they should be doing, and they're slowing traffic down. So they're taking the speeders, and they're saying, you're going too fast, I'm going to give you a ticket. It slows traffic down. Miraculously, we don't have fatal or serious crashes. So then I started saying, well, let's start introducing factors like how many crashes happened on a given road segment where the State Highway Patrol officer on the crash report just checks the box, says, well, the occupant wasn't wearing her seatbelt. That's it. Or one of the occupants was an older, over 65 or younger, less than 21 driver. Or in their opinion, driving under the influence was a factor. This is not checking blood alcohol. This is not doing breathalyzer. This is just the officer's opinion of whether or not alcohol or drugs were related in the crash, right? So this is them sitting in their patrol car right after the crash, filling out a crash report, and they're putting in all the movements in the vehicle this way and vehicle that way, and they come to a little section on the crash reports. They say, it's just little check boxes. Was there an older driver involved? Yes. Do you think this was DUI related? Yes. Do you think speed was a factor? Yes. Were there any unbelted occupants? Yes. That's it. Not very sophisticated. Turns out, that's pretty useful data. So once I started looking at that data directly, kind of changed my modeling approach, said, wait a minute, instead of kind of this starting with engineering roadway characteristics and trying to predict these sort of interim outcomes, which then predict fatal crashes, why don't I just use these measures of these interim outcomes and go one step, right? And that's what this picture really kind of shows, is a change in the model, and it's more of an emphasis on driver characteristics and behavior as opposed to roadway characteristics and things of that nature. So it's a different way of looking at the data. And lo and behold, I went back to the drawing board in terms of modeling, and I refused to do the AI approach again out of just a matter of principle because I got burned on the first time. So I just stuck with what I call the somewhat structured, which is a general linear model, and the very structured, which is a Bayesian network. Now, how many of you are statisticians? All right. That's my people right there. No. I'll put it to you this way. General linear model is pretty easy to implement, very easy to interpret. Require you to make some underlying assumptions about the data. Bayesian network, very hard to implement. Takes forever. But you can usually get to the same place over time. It requires modeling out that structure in the logic model explicitly. So we did it those two ways, and we got basically the same result. So from now on, I'm going to throw away the Bayesian network, not because it doesn't work, not because that method's not good. All of you out there that love Bayesian statistics, God bless you. It's great. I'm never going to do it again. But okay. Still got 30 minutes to go. So I'm going to present to you the results of the general linear model, but I want you all to rest assured that the Bayesian network shows basically the equivalent results. Same factors came up as important, same directionality, etc. Now, for the most exciting part of this whole presentation. Drum roll. Yeah, we're late on the drum roll. Here's what we found that were significant. And again, what I did was I went back and I put in all the variables I used before, and I added variables that were related to driver behavior, driver characteristics. And the modeling approach that I used was a stepwise selection, which is a fancy way of saying all possible permutations of variables were put in, taken out of the model automatically, and at the end of the day, the model decided which ones were the most significant predictors, right? So if lane width was a predictor, the model would go through and say, well, if lane width is in the model, then these other variables are no longer significant predictors, so we're going to kick them out. And then in the next iteration of the model, building the model says, well, I'm going to enter in one of the other variables. Oh, speed limit. Speed limit's important. Suddenly lane width is not important. So it gets kicked out. Speed limit's in. Then it just keeps cycling like that until it basically comes down to all the variables in the model are still in the model. They're significant. They're the most significant factors. That doesn't mean that factors that don't end up in our model are not important. I don't want anybody here running away saying HDR says that roadway characteristics are not important predictors of fatal crashes, all right? First of all, you should tell them it was HNTB. Little joke for my HNTB friends. No, I'm not saying that roadway characteristics are not important. What I am saying is, if you put all of these variables in the model, given that we have driver characteristics and behavior data in the model, those are the most important predictors of fatal or serious crashes. Roadway characteristics may be a predictor, but not as important as these other predictors, given that they're in the model. If we take these factors out, then it's likely that some other factors may come in. Now, I'll tell you, if we take these factors out, you're going to spend 6 months and you're going to run a whole bunch of models and you're not going to find any predictors, because that's how I started. But the key risk factors that the model came up with: number of crashes related to excessive speeding, unbelted occupants, driving under the influence, an older driver or a younger driver. Now, there were some other factors unrelated to driver characteristics or driver behavior. The total number of crashes, right, which makes sense. If you got a road segment where there's a lot of crashes, you have more of a chance to having a fatal or serious crash. The length of the segment, which also kind of makes sense. The longer your segment, the more chances you have for a fatal or serious crash. Functional class, and then whether it was an urban or rural geography. The key takeaway for me on this is that all of you are probably sitting there thinking, well, okay. Yeah, model did what I kind of would have thought it would do. And you're all a lot smarter than I was, because I didn't have these factors in the model to begin with. And I don't think, as we saw with a show of hands, that anybody should be shocked that these are factors that predict where fatal or the number of fatal or serious injuries are going to happen. They all make sense. And that's kind of the point, right? Makes sense. I'm not saying anything that anybody's going to say, wow, look at that. But what I am saying is these factors are predictive. How predictive? Pretty predictive. So what you're looking at here is a scatter plot on the left. The red line is sort of a reference line, and all the little blue dots, or blue circles, are actual points. And we're looking at actual number of crashes versus the predicted number of crashes for every one of our 1,829 segments. And the big circle at 0 is because there are a lot of segments where there aren't any crashes, any fatal or serious crashes, which is one of the challenges of modeling this. But at the end of the day, when you look at this model fit, it fits pretty good. It predicts the number of fatal or severe crashes right on the dot, roughly 60% of the time. And if we're within plus or minus one crash, roughly 90% of the time. Now I know what you're thinking. Ben, you're running these estimates on data that you use to build the model. True enough. But we took this model for these two districts and we ran it on a completely different district where all we did was take the model parameters and run it on that district. And we still came up with roughly the same outcomes, a little bit less. So in the other district, which was District 6, which is in the far southeast corner of Minnesota, it's a pretty rural district, we were able to estimate the fatal and serious crashes for each segment exactly, roughly 48–49% of the time. And if you count it within plus or minus one fatal or serious crash, that number jumps up to about 83%. Not quite as good, right? But still pretty damn good. Importantly, when we go to take a look at roadway segments, and if I look at the top 20% of segments, so the ones that we're estimating the highest number of fatal or severe crashes, or we convert the number of crashes into a probability of at least one fatal or serious crash. If I look at the top 20% of segments, those with the highest probability of a fatal or severe crash, that 20% of segments accounts for roughly 62% of all fatal or serious crashes. And that number holds up whether we're talking about the data we built the model on or this other district where we applied the model. Relatively the same level of predictability in the top 20% or top 10% or top 15% or whatever percent you want to look at. So let me say that again. We take the model with the driver characteristics and behavior characteristics. We apply it to road segments in another district. We calculate, the model spits out the number of predicted and fatal crashes that are likely to happen on that road district in the next 5 years. We went back into time on the next district. And when we did that, we were able to convert the predicted number of fatalities or serious crashes into a probability. And when we look at the top 20% of all road segments, we're capturing roughly 62% of all fatal and serious crashes. So I know one of the questions that district engineers get asked all the time is, where are you going to spend your precious dollars? And I would argue that what this model does, while it doesn't and shouldn't surprise anyone, what it does do that's a little different than what the traditional safe systems approach does is it gives you a way to target exactly which road segments you should spend dollars on. So what are we doing next? Well, we're trying to operationalize these findings. And we're building a dashboard, and we've built a dashboard, I guess I should say. And the district engineers are starting to use this dashboard. And what the dashboard basically allows you to do is select any one of the road segments over the course of 5 different MnDOT districts and look at what the probability of a fatal or severe crash is going to be for that given road segment or that group of road segments in the next 5 years. Then you can go into the model and go into this dashboard and you can look at things like what types of crashes are happening and where they're happening. You can look for clusters. You can do all of the things that we would do as engineers, right? So you can still do your forensic analysis on the crashes if you want and figure out if there's an engineering solution. For example, if there's a road segment and you see that the model is predicting that it's a high-risk road segment for fatals or severe crashes. The nice thing about a general linear model is the model parameters give you a lot of information about why the model is predicting that a given road segment is at an elevated risk. So if you saw that the model says, hey, this road segment's at elevated risk because it has a high number of crashes where their young drivers are involved. So as an engineer now, instead of diving into a problem blindly, I can say, well, wait a minute, is there something about this road segment that's making it hard for younger drivers to traverse it? Maybe there's a tight curve, maybe there's a change in elevation, there's a hill, there's a hump, I don't know what it is, right? But the model will start to provide you with information that you can then use to guide your engineering. So that's pretty cool. The second thing that the model does is it allows for operational and looking at citations along with crashes, right? So we're trying to engage more than just the engineering discipline. We want to engage enforcement too, because maybe there's an enforcement solution, right? So if you look at a given road segment and you say, wow, there's a lot of crashes by younger drivers, and you're an engineer and you say, I have no idea, we can't figure out why younger drivers are crashing. Maybe the distribution of crashes among younger drivers is pretty uniform across that road segment. If you go look at citations, maybe enforcement's the problem, right? Maybe you're not enforcing, or you're not having enough stops throughout that whole road segment. So these figures are just figures of what the kind of information you can get from this operational tool. There's a whole bunch of them. The most important thing is that because we're doing this, and because we have the ability to predict sort of ahead of time where a fatal or serious crash is going to happen, and we know and are able to say what's driving that prediction, whether it's DUI, older drivers, younger drivers, seatbelt use, or speed. Now not just the district engineers can be involved in thinking about interventions, all four of the E's can be involved, right? So the engineering can be involved, enforcement can be involved, engagement can be involved, and emergency response can also be involved. Right? So when you're looking at a given road segment and you see all the fatal crashes happen at the north end of the road segment, and you go back and you look at the EMS records and you see that they took all of those people because it was on the border of an EMS patrol area, they took them all to the hospital way down here at the southern end. You say, wait a minute, there's another hospital that's like 2 miles away. Probably, maybe, could have saved that person's life if we would have taken them to the other hospital. But because it was part of that patrol area and they were affiliated with this hospital, that's where they went. So the beauty of this model is not that it's the be-all, end-all model in the world. Although I am extremely thankful that we were able to come up with something. The beauty of it is that the model does a pretty good job of predicting locations. And I feel confident enough in the model and its predictions to say things like to the state engineer or to the captain of the State Highway Patrol, if you don't do anything on this, given these high-risk road segments, you're going to have X number of fatalities or serious injuries in the next 5 years. And so I've cut it down to, specific things. I went to the top most at-risk road segment, and I looked at the State Highway Patrol captain, and I said, look, we're predicting you're going to have 15 fatal or serious crashes on this in the next 5 years. And that could be wrong. It could be 14, or it could be 16. Somewhere between 14 and 16, right? But if you don't do anything, if you don't change anything, you're going to have between 14 and 16 crashes, fatal or serious injury crashes on this road segment. So it really is a tool to kind of say, well, wait a minute. How should we spend our dollars? The 20% highest at-risk segments cover 63% of all fatal and serious crashes. So instead of us going through a forensic analysis of crashes and saying, oh, here's an engineering solution, now let's apply that engineering solution to all of the roadways across Minnesota that look just like that intersection. What I'm saying is, let's go to the top 20% at-risk road segments and apply our money and our efforts there. And if we did that, we're going to cover roughly 63% of all fatal or serious injury crashes. And it may be 64%, and it might be 62%, but somewhere in that ballpark. Right? Okay, so what's next? Well, what's next is continue to try to operationalize this model. I showed you a brief glimpse of the tool that we've built. It's really now a matter of nothing to do with statistics anymore, nothing to do with data collection anymore. It really is, are we going to act on this information? And so what are we going to do? And that's really what the next steps are. And anecdotally, I can say that we're already starting to act on the information, and we're already starting to make a difference. I can't tell you with concrete numbers because it takes a while to see the change. It'll take a couple of years. But just by bringing together law enforcement and the engineering and the engagement communities sitting in a room looking at high-risk road segments together, anecdotally, I can say we've already started making a difference. Sorry. We looked at one road segment, and there were an awful lot of crashes with older drivers. And the district engineer said, well, we reduced the speed limit there, you know. Speed limit's low, and I'm getting complaints that the speed limit's low. And enforcement says, well, you know, we're stopping people, but we're not stopping them for speeding. And the advocacy group says, well, here's the complaint that we're getting from our older drivers. And I'll let you figure out which advocacy group was in the room. They're having trouble gauging the distance between oncoming vehicles, and so they're making left-hand turns into their cottages on these lakes, which they don't go to every day. And they're having trouble gauging the distance. So they turn left, and that's why we have fatal crashes, because they get broadsided by oncoming vehicles. Okay, wait a minute here. Just being in the room, then the district engineer says, well, I can do something about that, right? I can put a stoplight in, we can give turning movements, we can put a turning lane in, et cetera, et cetera. I don't know what all the treatments are. But the value of what we've been able to do here is not just that we created a model that's the be-all, end-all. Because again, I think everybody in this room understands that the factors that we're saying are predictive of fatal or severe crashes are factors that if you sat down and thought about it, come to mind. Seatbelt use, speeding, DUI, young drivers, older drivers, right? I mean, these are not, nobody's gonna say, wow, Ben, you created something new. These are all factors we know about. The beauty of this model is now we have a way and data that shows and some guidance on which of these factors is important for which road segments in terms of predicting fatal or serious crashes. And so now it's up to us to do something about it. And that's the beauty of this project. So I'm hoping that come back in a year or so, and we're going to show that the fatal and serious crashes, instead of this upward climb that we've been seeing over the last couple of years, by changing how we're approaching this, instead of doing that detailed forensic analysis, we're going to these high risk and risk as determined by driver characteristics and behavior, and we're imposing solutions there and driving down our fatal or severe crashes. And that's all I got. So happy to answer any questions. Oh, question from a statistician going to be trouble for me. I feel like I'm in my dissertation again.
I don't know. Yeah, here you go. It works. Yeah, I think I enjoyed this session because I love data, and this is kind of my favorite. But I'm biased because I did my PhD in transportation. So thanks for this. I have two questions. You mentioned 4 E's, and some people include education as the fifth one sometimes. Do you have any data sets kind of showing the education level? Some states use failed DMV tests or reoccurring offenses to, penalties, kind of getting speed tickets twice to be able to show if people learned anything from their, first offense. And my second question is about the model. Do you have a stratified version of it for different area types or facilities or speed intervals?
Okay, so answering your first question, and the first question, if I rephrase it in my own speak, is do we include any kind of education parameters as another occupant or driver characteristic? And the answer is we didn't. We probably could. We could go into, for example, crash records and look at how many times a given occupant was in a crash, but the reason we didn't do that kind of thing is because of the privacy. We could also go into municipal court records and look at citations and find out who has what kind of citations, whether there's a repeated pattern. We didn't do that, again, mostly because of the privacy. In terms of your second question, do we have stratified versions of the model for different types of areas? I would say no, we really have one model, but it does have factors associated with urban, rural, geography, functional class. So we are able to incorporate different kinds of geography. And we looked at including variables like land use, predominant land use, and all those other factors. So they didn't end up in the final model, but we did have urban, rural, suburban, or small urban, whatever you want to call it, as factors in the model. And that does provide us the way to kind of adjust the model given those factors.
Thank you for this presentation. It was really great. So I do also have like a couple of questions. The first one is related to the identification of the hotspots toward the end of the process that you did. I believe like you used the developed SPFs and get the predicted crashes and then like identify these hotspots. So did you take it to the level to identify also sites with promise or not? This is my first question. Second one, did you test any interactions within the developed model or not?
Okay, so I'm going to answer the second question first, and then I'll go back to the first question. We did look at a bunch of interaction terms, and it gets complicated pretty quick, as you might suggest. In the end, we went with a main effects only model because we weren't seeing that interactions were really giving us a lot more new information. And really one of the things coming out of this model that we really wanted to see was ease of interpretability. And anytime you have those interaction terms, it can get a little more challenging to interpret. And for the bang we were getting for the buck of including them, we just decided to leave them out of the model. I'm not sure I have a great answer for your first question. I guess what I would say is what we did was we used the model or the Bayesian network, whichever way you wanted to do it. We did it both ways, to predict the number of fatal or severe crashes for every segment in the next 5 years. Then we converted the predicted number into a probability. And that probability is the probability of at least one fatal or serious crash on that road segment in the next 5 years. And then we ranked basically top to bottom all road segments in the network by that probability. So we have, for every road segment, we have characterized it in terms of that probability of at least one fatal or serious crash. So just because I talk about the top 20% doesn't mean that all the rest of the road segments don't have an associated risk level. We selected the segments carefully. You gonna let me get off with that? No? Okay.
Darts?
The reality is defining the road segments is where the sort of the art comes in. And the reason is, and I'm gonna take you all back to statistics class, and I'm sorry, but I'm gonna do it. If you remember your discussions about rates, the way it works is, and a rate is basically the number of events per some interval, so whether that's length or time. In this case, it's length, right? And the way that rates work is, if you make the length small, really small, then the probability of an event happening is really small, right? Because think about it, if you have a car driving down the road and you say, that car is gonna stop in this 1 foot section, right, with the front wheel. Well, the probability of that happening is very, very small. But if you say if it's gonna stop in this 100 feet, then the probability of that happening goes up, right? So length is directly related to the rate. And the rate is directly related to probability. So I promise I'm answering your question, I'm getting there. How do we define the road segments? Well, MnDOT has road segments defined down to the 1/10 of a mile. So if we just use their 1/10 of a mile, it's really easy to come up with a model to predict whether in that 1/10 of a mile there's going to be a fatal or serious crash. The answer is always no. Because the probability of a fatal crash in a 1/10 of a mile is very, very small. So what we did was we started with looking at logical road segments, right? So from major interchange to major interchange. We built up the road network basically the way that you would view it if you were a normal person outside of transportation, right? So if I was to give you directions how to get somewhere, well, go on this major road to the next major light and turn right, right? Well, okay, so that's a road segment, right? Going from this major light to that light. And then we looked at those and we wanted to try to have some uniformity. And on average, our road segments are roughly 6 miles, 6.5 miles in length. There are some that are short, there are some that are up at 15 miles, but on average, it's about 6 miles. So that's how we kind of did it. We looked at major crossroads. And then if we found that the major crossroads were too close, we added them up together until we got to roughly six miles on average.
Okay, we have time for one quick question. Anybody? Okay, let's hear it for Ben then.